We are live, sir.
Okay. Good morning, everyone, and welcome to the second session of the keynote lecture today. We have Professor Sunita Sarawagi. She needs no introduction and is well known in the domain of computing and science. So, without further delay, I would just like to quickly introduce her to the audience. Professor Sunita is the Institute Chair Professor of Computer Science and Engineering at IIT Bombay and is also the in charge Center of Machine Intelligence and Data Science. She received her bachelor's degree from IIT Kharagpur and master's and PhD from the University of California at Berkeley. She worked at Google Research, CMU, and IBM Center. She was awarded the Infosys Prize in 2019 for Engineering and Computer Science and the Distinguished Alumnus Award from IIT Kharagpur. Later, IIT Bombay gave her the Professor H. Mathur Excellence Award in Applied Sciences. She was named to the Indian National Academy of Engineering in 2013 and she was selected as the 2021 ACM Fellow for contributions to statistical machine learning for information analysis, extraction, and integration. She has several publications, including Best Paper Awards at ACM Sigmod, VLDB, ICDM, NIPS, and ICML conferences, and also several patents. She has served on the board of directors of the ACM KDD and VLDB foundations. She has also given many invited talks. She was the program chair for the ACM KDD 2008 conference, research track co-chair for the VLDB 2011 conference, and has served as program committee member for SIGMOD, VLDB, SIG-KDD, ICD, and ICML. She is also on the editorial boards of ACM Thoughts and ACM TKDD journals. She has served in several award committees such as the Early Career Researcher, Best Paper Awards, Innovation Awards, and Service Awards. Her topic of interest spans several fields, including machine learning, data analytics, databases, and statistics. Currently, her focus is on sequence models for text and time series, domain adaptation, effective human intervention in learning, graphical models, and structured learning. Please join me in welcoming Professor Sunita at the DICE program. I now kindly invite Professor Sunita for her keynote lecture.
Thanks a lot, Professor Uttam. I would like to first share my screen. Okay, I hope you can see my screen.
Yes, we can.
Yeah. So today I'm going to talk about the state of machine learning when it is applied in the real world setting. So even though currently AI and machine learning is one of the hottest fields, not just of computer science, but I would even say most of whole of sciences, uh, up until say 12 years back, that was not the case. Machine learning was like a lab field which involved a few researchers, and there were a few commercial houses, notably banks and all, which used machine learning for well-defined operations which were carried on within the boundaries of their organization. But that's not the case anymore. Now, machine learning impacts many aspects of of all of our day-to-day living. It impacts how we do science, it impacts how we do commerce. And in this talk, we are going to reflect on the challenges that the lab field faces when it meets the real world. So the core operation in machine learning is simple. You take as input an X. So this is the input X, which can take just about any form. And you output a label Y, which often is a single discrete variable. And you learn the X to Y mapping using what are called training examples, which basically contain several input output pairs which somebody has supervised to be correct. When the input X is an image, then this core simple model has several applications. For example, in surveillance, Some of you might have heard that in IIT Bombay there are a lot of panther sightings. So if you have a well-mounted camera, then maybe you can use such a model to tell apart panthers from dogs. There are applications in the health domain. For example, people are using AI diagnostics models, for example, to tell apart normal retina from diabetic retina. When the input is text, then you can do all kinds of things. For example, you can route uh, text like incoming messages based on the topics on which the messages might be about. And there are thousands of several of such applications in the real world across for in commerce, like say for forecasting, recommendations, advertisements, in the sciences and so on. So in spite of these really varied applications, the core algorithm for creating these machine learning models is very simple. You sort of assume that there is a latent distribution jointly between the space of inputs, which we are denoting as this x, and the space of outputs, which we are denoting as this funny y. And what you get to see in the training data are just some samples from this latent distribution. And all you really need to do during so-called the training process is to learn the conditional distribution of the y given the x. Now, you learn this conditional distribution given finite data by taking a bunch of steps. The first step is to choose the type of classifier that you want. And this you can think of as choosing a function which is typically a continuous function, but not always, which takes as input an x, and it has these parameters theta, and this function therefore is often like a continuous function of the thetas. And this function basically is what you can easily transform, say using a sigmoid transform, to a probability distribution of the on the y given x. And now you use the training data to find a good value for the theta. And there is this age old principle from statistics which says that a good theta is one which maximizes the probability of the given training samples. So you try to find the theta which over all the training examples will maximize the log of the probability of the y given x. So this is a continuous optimization problem which you can solve using gradient descent for the functions that you choose, which are supposed to be continuous and differentiable in theta. And there are theoretical guarantees on why such a f that you have learned and the theta that you have fitted using this step of maximum likelihood estimation should be useful, in the sense that it should give you good predictions of y, or it should output mostly correct y's when you give to it an input x star which was not seen during training time. There are guarantees. You can sort of say that if this is the type of the function, and if I give so much amount of training data, then what is the probability that the predicted label will be correct, assuming that the data which you apply it on comes from the same distribution from which you got the training data. And now there have been many different forms of such functions. So this is basically what the history of machine learning is. There is a long history of designing forms of such functions starting from the 1950s. Many different approaches have been proposed, each of which have gone through their boom and bust cycles. So starting from perceptrons to logistic regression, neural networks. I mean, yes, neural networks have been around for a long time. Only now they have become really they got their fame. Knife-based linear discriminant analysis, support vector machines. Some of us have seen the boom and bust cycle of support vector machines. Gradient boosting, random forests. So, many different classifiers exist. And what people now know of deep learning is just one of this very large number of functions which have been proposed. But across all these different methods, one sort of one method which has sustained for the longest time is this very simple logistic regression classifier, where the pipeline was as follows: you take the input x, you use a human being to design domain specific features. So these are sort of, we base on our understanding of the problem domain, think of signals which we feel would be relevant to the prediction of the y. And then the classifier itself is kind of very simple. You sort of so the human has taken the input x, which could be, remember, an image or a text, it could be an audio clip, and then we use our expertise of the domain and some understanding of the math of the input x, and we design a set of n features. So x2, x3, xn, up to say maybe n features. And the only thing that you do during learning is to just assign weights to these n features. And once you take a weighted combination of these input features, you get a real value, and then you applied a simple sort of thresholding function to convert that real score into a discrete binary class label when we are talking about binary classifiers. And this method easily extends to the case where the output y has more than two values, so like general multi-class classification. So the advantage of this very simple approach is that it gave rise to a very tractable training objective. So finding the parameters W0 through Wn so as to maximize the likelihood of the data gave rise to a convex training objective. And therefore the training process was reliable, it scaled trivially, and this is what fueled many applications behind, say, ranking results in search engines. So the biggest search engine companies depended on very simple logistic regression classifiers to decide on what to recommend to people and how to rank results, in retail, in banking, for deciding on loan approvals, etc., etc. So this has been sort of the case up until, I would say, 12 years back. And as I said earlier, neural networks have been around, and neural networks can just be thought of as just sort of a cascading of the linear functions I just presented earlier. That you don't, when you go to these neural networks, you don't depend on a human to extract the domain specific features, but rather you just feed the raw input, and then you create many different layers of such linear combination of the inputs coming from the previous layer, followed by a nonlinear thresholding function. And you do it both layer wise here, and within a layer you have many such transformations of the input. So these have been around for like 40-50 years, and they had many good theoretical properties in terms of the class of functions they could represent. It can be shown that just a one layer neural network with one hidden layer, it can be like it can be a universal function approximator, and it therefore has high capacity. But the problem was that it was very difficult to train these old style neural networks, and because it had too many local minimas, unlike the previous function that I said, which gave rise to a guaranteed convex training objective. That was not the case when we are using neural networks. So they were considered too hard to train, too unstable, too slow. But that was the complaint up until only 2010. And around 2011, 2012, a bunch of die-hard neural network researchers continued to engineer the training of these multi-layered cascades of linear functions followed by a small non-linear activation. And they finally hit a jackpot around 2012. where and then a few more things happened in parallel. A lot more training data started becoming available. On the hardware side, people realized that GPUs do not need to be used just to drive screens, but rather they can be used to efficiently convert training algorithms like gradient descent training algorithms into large matrix operations which can be executed fast on GPUs. And there were a few more advances in the design of the numerical optimizers. So instead of using batch gradient descent, people started using more and more stochastic gradient descent methods, and also adaptive setting of learning rates, etc., gave rise to some advances here. And then the neural network itself, the architecture was engineered. People found that the nonlinear activation from one layer to another, instead of being a sigmoid function, if it is made a ReLU network, you get better training, because then the gradient follows at least in one direction. And then people found the power of dropout and the increased capacity one gets by having deeper, wider neural networks. And that suddenly, the convergence of all these different factors gave rise to neural networks providing record breaking accuracy in many difficult tasks. And then we started seeing a lot of success stories. The first success story came from the vision community, where there had been this long-standing competition on the ImageNet data set, where the task is given an image. Here you see a bunch of thumbnails of such image. You have to identify the objects that are present in that image. There was just one object that you have to label in each of these images. And this competition had been running for a while. In 2010, people found that the error that they could get on this ImageNet classification task was around, say, 28%. And then the subsequent year, again, it was improved slightly with some more hand feature engineering and maybe using support vector machine classifiers than what perhaps was used earlier. And then, but in 2012, you saw people just suddenly saw a huge drop in the error, which went down from like almost 25% to like 17%. And this huge drop came with the first deep learning model used for image classification. And then from that 2012 onwards, every subsequent entry reduced the error of the previous entry, and they all used deep learning. And in 2015, by some very crude estimate, people found that perhaps the vision, the image classification model on the specific ImageNet data set was giving them lower error than what a human would obtain if they sort of saw these images and tried to assign labels to them. Same story for another very compelling task, which is using deep learning models for speech recognition. So using that, you can convert audio to text. And here again, there was this well-known competition on a conversation data set, which is called the switchboard data set, which stored telephone conversation of native English speakers. And this on the y-axis here, you see again word error rate. On the x-axis is different years. And so in just slightly before 2012 was the first deep neural network model. And every subsequent, so that was kind of a hybrid model. It used a bit of hidden Markov models and a bit of deep learning. And then every subsequent year, there was a better neural architecture for processing audio data, and there was a better blending of the language models, which is the clue that you get from the background text with the audio signal. So much so that around 2017, even for the speech recognition task on the switchboard data set, the word error rates hit the human level. And so now the neural model can provide lower word error rate than what a human can. Another application, not as mainstream but very interesting, is grammar error correction. So now I'm sure all of you have been bombarded by Grammarly and other applications which automatically correct your grammar errors and spelling mistakes, etc. And even that was made possible because of deep learning. So even we had a paper in EMNLP 2019 where we got very close to human level performance, at least on that benchmark, using an interesting deep learning model, which did not use the standard sequence to sequence model. So this was another application. So with all these success stories, deep learning suddenly became the main actor, and we entered into this age of mega models, where uh, you know for more and more of these so-called classically difficult recognition tasks, be it recognizing objects in images or text in spoken audio, it was possible to use deep learning models. But characteristics of these models is that they were huge. They, like a typical deep learning model, would have used like billions of parameters, and to train these billions of parameters, they would require a huge amount of label data. And of course, these two together also meant that they were very power hungry. And such kind of resources, though, were affordable only for a few resource rich organizations which had access to a huge amount of data. And then they had access to huge amount of compute, and they could use lot of energy. Each of these data centers are extremely energy hungry. And of course, you need to hire the best of deep learning engineers, I would say, who would then create these mega models. And because doing this was not easy, both in terms of the amount of resources that it consumed, and also the kind of human expertise that was required to engineer and fine tune such models, the hyperparameters of such models. So we entered the situation where a few resource rich organizations train the model, and then the rest of the world is using those models. And now, when the user community of a model is very disjoint from the entity which trained the model, the classical assumption for the validity of the training algorithm that is used for machine learning models no longer applied. So the main assumption for a machine learning model to do well on unseen examples was that the unseen example should be sampled from the same distribution as the distribution from which the training data is sampled. But suppose if the model is trained by some big organization, and then somebody is sitting in, say, maybe a lab in India, or maybe even a bank in Africa. There are people all over the world now who download these pre-trained models to use it, but then we are not guarding against their using the model in a scenario which is different from the scenario in which it was trained. We have several challenges which come up. So only a small fraction of the deployments of uh, a state of the art machine learning model is in the ideal scenario. And the success stories, the three success stories that I mentioned just now, these were all in the ideal scenario where there was a well defined benchmark, and the training data was a subset of that benchmark, and then the test was from the same benchmark. So in this very ideal scenario, you can claim that yes, deep learning is providing you superhuman accuracy. But when you actually release it in the wild, and when the train and test distributions do not match, there are several challenges which come up, and we are going to group those challenges into three categories. The ones which come out when the deployment distribution is a very narrow slice out of the training distribution. The second here is when it is used in a scenario where the sample is totally outside the training distribution. And the third is when somebody is, adversarially trying to create an example which is outside the training distribution. Okay. So we are going to go through each of these sort of diverse challenging scenarios in the next few slides. So in the ideal scenario where the training and test distributions match, this is where we see most of the impressive success stories in the press. But now we are going to talk about the first kind of non-ideal application where you deploy a machine learning model in a narrow domain, which is a very small fraction of the training distribution. And here, in order to kind of use the model to its full capacity, you need to do an adaptation of the model. So suppose, so let me give an example. Suppose you have a speech recognition model, which was, say, trained on, speakers who are like native speakers. And now we want to use that speech recognition model in India. And, the accents that different people in different states of India have is very different from, say, the accents of an American or a British speaker. And so now you need to even though, when a large company trains the model, the speech recognition model, on some subset of its data coming from, say, Indian speakers of English, but when you deploy it solely on Indian speakers of English, then this model, which was trained on a much larger universe of data, might be suboptimal for a smaller uh, part of the distribution in which you are interested in actually deploying the model. Likewise, consider the example of translation. There are now many translation models which are available in the public, and some of the standard data sets for training the translation models were obtained, say, from parliament transcripts or from news sources. And now, if you use a model which has been trained on such corpus, say, to do translations in the medical domain, so you want to use it to maybe apply translation of conversations between patients and doctors, or for translating medical transcripts. So this data is very different from the training distribution on which the model was trained. Another example is a language model. Say, suppose if you want to create a language model which will assign embeddings to words, and you create those, you create the word embeddings using, say, the whole of Wikipedia, but now you are only interested in applying those word embeddings for solving some NLP tasks on a physics corpus. Then again, you will need to do some more adaptation for the model to be optimal for the physics corpus. And actually, domain adaptation is particularly relevant to us for applications like speech recognition, translation, language understanding, reading comprehension, question answering. So now there are a lot of these AI-driven tools which are available for people. And in India, of course, this one of our defining characteristic is diversity. Even for a particular mainstream language, there are several dialects, there are several accents, and we need to be able to very quickly adapt a model which is trained on some universal corpus to a particular subdomain where we want the model to be particularly suited or optimized. And another challenge is that for each of the subdomains in which we might want to deploy a model, we may not have too much labeled data in that subdomain. And the only solution is therefore to design effective domain adaptation model rather than to attempt to train a separate model for each local region. So here is the formal domain adaptation problem. We are given a trained model theta. So this model has been trained on a large data set D. And we are given a very small amount of labeled data in a target domain Q. Now, L is not large enough to train a good model on its own. And there exists a training domain which was present in the training data, which we are calling as DJ, which is a subset of this capital D, which matches the target distribution, but we do not explicitly know what is the DJ. We have to discover the DJ using L. Okay. And our goal is to train a model which provides the best combination of the universal model, which is theta, and using the limited amount of label data L in the target domain. And the other interesting part is that even when the number of parameters is very large, if samples from a domain DJ are a very small part of the overall training data, you will still find that the model's theta would be suboptimal for a target domain Q. So that's why it's very important to adapt even when you have seen such examples in the training data. So to motivate this point, this claim further, I will talk about a case study we had with just this very down-to-earth task of training word embeddings. As you know, word embeddings assign to each word in a language a real vector so that words with similar meanings or which appear in similar context are grouped together in that real space, okay, from which the word embedding vectors are assigned. So we will think of now the model theta as just denoting the embeddings of words. Okay? And now suppose you train the embeddings of words on the Wikipedia corpus. There is a well-known algorithm called word2vec, which can learn embeddings of words. Okay, so you apply word2vec on the entire Wikipedia corpus, and you get the embeddings of words. Now, Wikipedia itself is a union of several topics, but we are, let's say, interested only in physics documents. But but the amount of physics documents perhaps is not enough. So we want to somehow also make use of the entire Wikipedia, because physics is not just terms which are only relevant to physics. It also might be talking about understanding standard language. You need to both understand, you need to have the background knowledge of English along with physics specific knowledge in order to fully comprehend a sentence from a physics textbook. So we cannot say that the rest of Wikipedia is irrelevant to our goal of learning embeddings of words in the physics corpus. And another big source of challenge is that there are words which have multiple senses. So if you consider a word like potential, the standard meaning of potential is similar to words like possibility, capability, impact, and so on. Whereas if you are talking about physics, then potential has, the prominent meaning for potential is closer to words like kinetic, voltage, and energy. And but there are other words like cat, which might have the same meaning in the global and the physics corpus. But on the other hand, if you are interested in, say, the Unix corpus, just things to do with operating system concepts, then the word cat in the global sense would have a very different meaning in a corpus about cats, about files and commands, where cat means concatenation. So a standard solution to handle such domain adaptation is fine tuning. So in fine tuning, you initialize the model first, with the global values of the parameters, and then you use the limited label data with a little bit of regularization to keep the modified theta close to the original theta, and you do some more epochs of gradient descent training to get your adapted parameters theta. So this is what is often used in practice. Now, in this talk, what I want to persuade you is to think of approaches other than fine-tuning, because fine-tuning in many situations is actually not that effective. So one big problem with fine-tuning is that it's kind of tricky to implement in practice. If you do too much fine-tuning, you might be subject to what is called catastrophic forgetting, which means that in the theta, whatever useful knowledge that you extracted from the whole of the training data, that would be wiped out if you do too much fine tuning on this tiny label data L that you have in the new domain, because that data is so biased and small. But if you just keep on doing your training epochs on that limited amount of label data, you might wipe out the useful information you have learned from T. This is called the catastrophic forgetting phenomenon. And if you do too little fine tuning, then you have not adapted enough. And the big challenge is that not all the thetas need to change. That is what I've been saying earlier. Some of the thetas, this word nucleum, it has the same meaning in the global corpus and in the physics specific corpus. So you don't need to change that, whereas the word potential needs to shift when you go from the global corpus to the physics corpus. So what in fact we found that if you fine tune theta with a small amount of physics data, then either you forget too much or you have not adapted enough. And if you somehow magically come up with the right number of epochs, then the best you can do is is sort of just ignore the theta and just train the word embeddings on the physics corpus alone. Okay, so that is sort of just train the thetas from scratch. So we found that instead of fine tuning, if you do this other thing, which is to basically revisit the training data. So you have a limited amount of label data L, but then you revisit the Wikipedia corpus and just using plain IR techniques, just find Wikipedia documents which have significant overlap with a few sample physics documents that you might have collected, which is what we are calling L. So you find the subset of your training data which is similar to the limited amount of label data you have on physics. And then you retrain the model on the subset of the relevant subset of the training data, and of course the limited amount of label data that you have. And this was by far, it's a very simple idea, but it was just so much better than the typical approach of fine tuning that everybody does, that we had to write a paper about it. Okay. So the key message from this part of the talk is to say that in sort of globally trained models, knowledge about non-dominant senses of words could be obliterated. And by the way, I gave this example of word embeddings, but the same phenomenon is observed even in language models like, say, BERT. So if you have trained a BERT model, you download a trained BERT model, but now you want to use it to solve the named entity recognition problem for physics documents or for medical documents, then you are much better off repeating the pre-training steps of BERT with unlabeled physics or unlabeled medical documents first, before you apply it for the named entity task recognition task, and you actually do task specific fine tuning of the BERT model. Okay. So this is the key message here. But now, of course, there are some scenarios where you do not have access to the source data. And so you cannot always revisit the training data for improving your fine-tuning step. So in such cases, what can you do? Okay. So as I said, if you just fine-tune with the theta with a small amount of label data, you might encounter high variance. And so what else is available to you? So another trick which has been ignored very often in sort of providing frameworks for fine tuning is to understand that the training data itself often comprises of a union of domains. So now we think of the label training data as not like IIT samples, but rather a union of several domains. So if we know the domain boundaries in the training data, then maybe we can learn how to adapt better. So this is called the meta learning step. Okay, so there have been many approaches proposed for meta learning. So the main so these are approaches like these are mammal, snail, deep state. I'm just listing a few of them. But each of these approach has some of the other limitation. For example, this mammal, which is this memory agnostic meta learning, so that actually requires nested loops during training, and the training is a bit tricky there. Snail was supposed to be also a very good method for doing sort of using multi-domain data for learning to adapt, but it requires you to do a expensive self attention over per domain data. And deep state is another model which was used to kind of to generate per domain parameters using another neural network. So each of these were kind of considered to have some or the other limitation, and we had proposed this one method which we felt was kind of better suited for certain kinds of regression tasks, so which we call online adaptation method for regression. And here the main idea that we proposed is that instead of trying to adapt all the parameters, because then there are sort of several challenges, what we do is we partition the set of parameters into the set of shared parameters which are not modified with available label data, and then we have this domain specific data. So for each domain in your, suppose if you have like say four domains, I'm just showing it by four different colors. For each of these four domains you would have separate parameters, and the main trick we are proposing is to carefully choose the domain specific, this split of what we will consider as domain specific and what we will consider as shared. We'll have to design and carefully choose. And in fact, for a particular regression tasks, we did the split so that the domain specific parameters could be trained without gradient descent training. You can get the values of the domain specific parameters just using a closed form formula. And then you did not need to use nested loops for jointly training the domain specific parameters and the shared parameters. And other additionally, the domain specific parameters, we were thinking of it as a sufficient statistic, which could be sort of accumulated online. So in particular, the domain specific parameters was like a linear least square model, which was residing on top of a standard neural network, and the sufficient statistics required to train a least square model was incremental, and it worked very nicely for a time series forecasting task that we were trying to solve. So basically here the key message we are trying to say is that in some cases, in particular for regression tasks, one might want to think of domain specific parameters as just residing at the last linear layer, which can be learned in closed form. And this actually leads to better training dynamics and faster online adaptation than existing more elaborate meta learning methods. Okay, so this was about a domain adaptation, and actually I just see that I have only 1 minute left. Uh, so 45 minutes talk plus 15 minutes Q&A. So I might just take 6 more minutes and wrap up the rest of the talk. So the second point is about handling unknown distributions. So one big problem with modern machine learning is that it often very confidently gives the wrong prediction. And one of the scenarios when such high confidence wrong predictions happen is when you give to it examples which are outside the training distribution. So here is a scenario. Suppose if I'm trying to solve a two-class classification problems between red and blue points, and I ask you to assign a label for this star over here. If you just use standard learning techniques on these two sets of training examples, then it will be very tempting to call this red, to kind of design a decision boundary between the red and the blue points here and assign to it a label red if you are, say, just training a linear classifier. But a more careful method would say that no, I don't know what is the label of these examples, because it could very well be that if you showed me label data in this region, they might turn out to be blue, even though given the current label data, it's tempting to design a linear decision boundary between the red and the blue points. Okay, so this is the main message here, that ideally we should be able to find around each unlabeled points the density of labeled data around that point. But of course, it's very easy to talk about it qualitatively. In practice, it's really hard to characterize density of high dimensional objects, because in the very high dimensional space, every point around it has a lot of empty space. So characterizing sort of a useful characterization of px as relevant for the decision problem is very challenging, and many papers have been proposed for this, and it's an exciting area of research. And now, so this was one challenge we faced. And now when we thought about it, we felt that very often the out of distribution examples come not because of some errant outlier, but because there is some systematic domain shift. So when you are training data to be sort of from a union of k domains, but suppose if I tell you that, look, during test time you might see more such domains, then perhaps what we are currently thinking of OOD examples should actually be thought of as new domains which we did not see in the training data. Consider an example. Suppose if I'm training an OCR model with 20 fonts, but when you are training an OCR model with 20 fonts, any human being would know that 20 is not like a closed universe of possible fonts. If there are 20 fonts, there can be a 21st font, there can be a 22nd font. So the machine learning model should support generalization to new domains. Classical machine learning talks about generalizing to new instances to individual examples. Here, what we are arguing for is generalizing to new groups of examples, which we are calling as domains. So this is the domain generalization problem. And so we want to train models to be resilient to new domains. And this is another very interesting area. Lots of papers have been written on this. One well-known technique is domain adversarial network, which tries to train networks which do not have any domain input. We proposed a method in ICLR 2018, which we call cross-gradient training, which try to train the classifier with examples which are augmented with perturbations which along the directions of domain change. So this is the cross-grad algorithm we call, and you can find out more about it in this paper we wrote in ICLR 2018. But the key message I want to send here is that OOD detection, like detecting examples which are outside the training distribution, that should be an integral part of any machine learning model which is deployed in scenarios in organizations which are outside the training organization, to avoid embarrassing high confidence predictions. And classifiers can be sometimes taught to be robust to OOD detection by making use of methods for training domain generalizable classifiers. And domain adversarial training, while it sounds very good in practice, it sounds very good at an intuitive level, is often hard to implement. And sometimes you might be better off by training a more robust classifiers by augmenting your training data with hallucinated domains. So I'm going to skip this last topic on adversarial training and just go to the summary. So basically, in summary, I would like to say that training ML models is turning out to be extremely resource intensive, because of which now there is one organization which trains the domain and several users use it. And there is therefore the danger that the model might be used in distributions which is different from the training distribution. And there were three settings in which we discussed failures that can happen. One is when you are trying to serve a specific narrow domain. Then we talked about the problem of domain adaptation, and we tried to say that fine tuning is, even though it's the mainstream approach, there are other options you should consider. One is to revisit the source if you can, and the second is to use closed form domain specific parameters. The second danger scenario is when you try to deploy it in an unknown distribution. And here there is no distinct adaptation phase with label data. Instead, what we would like to do is to detect out of distribution examples, which is by itself a challenging problem, and reject examples which we cannot handle with high confidence. Domain generalization is one emerging area which plans for OODs which arise out of domain change using multi-domain data during training. And adversarial instances, I did not have much time to get into, but here the goal is to train robust models which try to minimize error with worst case perturbations on the training examples. This is also an area which invites a lot of research from the research community. So in terms of going forward, what we can say is that existing approaches seem like reactive post fixes to outdated models of training. Perhaps there is a need to rethink about how, number one, we design our machine learning models. Is it possible to create more modular components in these mega models, each of which can be interpreted, and therefore which by design will generalize in ways, and it will not throw surprises when it is sort of deployed in scenarios which humans consider natural, but which become challenging for machines. And another topic which I have not had chance to get into is training models for lifelong or continuous learning. This is another interesting area. And finally, many people believe that going forward, the only guaranteed way of doing good, of having robust deployment, is to train models which behave like humans, in the sense that which make predictions based on causal reasoning rather than just capturing correlations which are present in the training data. That's all. Thank you.
It was a wonderful session showcasing historical machine learning to state-of-the-art machine learning models from Professor Sunita Sarawagi. Examples ranging from neural networks to deep learning, speech recognition to grammar error correction, and listening to the age of the mega models was very fascinating and insightful. With the kind permission from the professor, we will proceed to have any questions.
Yeah, of course. Yeah.
So Professor Dinesh Babu has a question. Is there a connection between shared and domain-specific parameters and low-level and high-level, that is semantically meaningful parameters? It's also there in the chat box.
Yes. Yeah. Well, I would say these are orthogonal, right? I mean, although I agree that it might be easier to design domain specific parameters if they are semantically meaningful. But if you think in terms of but of course it's one of the reasons why uh, deep learning works well is the fact that the parameters are kind of allowed to train, and intermix in arbitrary ways. And very often, when we try to assign semantics to parameters, it becomes very difficult to mingle with the black boxy, undifferentiated neural parameters. So, yeah, so yeah, there is no explicit connection, but I would say that it might be easier for at least end user to decide on domain specific parameter values with limited data. They can assign better priors if they are also semantic. But then you will have the challenge of co-training a network with semantic and low level parameters, which might be which actually is often is surprisingly does not give you the best overall accuracy.
Ma'am, I have a small query. This is Shivkumar Malpaka.
Yes,
Uh,
yeah,
Ma'am, the query is from physics.
yes.
So recently there was one, say, satellite that was sent, Gaia, GAIA, and it observed billions of stars.
Mhm.
Okay, so before we could train and anything and say understand the data or make meaningful predictions out of the data, the labeling itself is a problem for such say, because there are billions of data points and each star is different. So is there
Yes.
any method which can improve the labeling itself?
Yeah, in fact there are lots and lots of this is another area which is extensively researched. And if you are talking about reaching out to the unknown, then by definition we cannot provide, this is an impossible task, providing labels for the infinite beyond. But for a more down to earth problem on the our immediate surrounding, even there coming up with label data is extremely challenging. People have so like even when you try to use crowdsourcing to assign labels, there are many tricks for introducing enough redundancy and and also cross checks to ensure that the labeling is correct. But if you also want to make the labeling efficient, then people have tried uh, to label with functions. So there is another area called labeling functions where humans register rules for labeling en masse.
Okay.
So providing labels which is both efficient and high quality is a long-standing challenge, and many ideas exist. Starting from active learning to crowdsourcing to using labeling functions. Yeah, this
Okay.
is yet another talk, I would say.
Oh, okay. Thank you.
Yeah.
There is another question by Ishan. He says, uh, when there are many different parameters and many different domains, is there a possibility of using classification techniques for partitioning?
Partitioning of what? I think I don't understand the question.
Yeah, Ishan, can you please elaborate a bit?
Partitioning of parameters. Okay. In I mean, so partitioning of parameters for what? I mean, why would you want to partition parameters? Do you want? Oh, okay. Now maybe I think I get the question. So if you have, like, say, a model, you have designed a network, then is there some general principle we can use to partition the parameters into domain specific and shared parameters, right? So people have tried to use maybe I cannot think of a paper right now, but I'm just thinking on the fly. One can always use gradients. You can you have a model, and now suppose if I give you data partitioned across domains, then you can see which part of the network is activated most for certain kinds of data, and then you can partition the parameters based on, let's say, the diversity of domains. If a particular parameter is equally well activated by several domains, then it should be shared. And the ones which are domain specific would be activated by only one or two domains. So such things could be used. Yeah.
There is one more question from Professor Sujit. So he thanks you for the wonderful talk, and then he has a very different type of question. He says that all areas of computing have had intractable, undecidable problems for a long time. These days, it has become mainstream to use ML to solve those problems. Unfortunately, we who are not trained well in ML often tend to use ML in a very non-rigorous way. However, getting on top of the entire ML literature is difficult, being involved in other areas. How to handle this issue?
Yeah. So, that is very good question, Professor Chakrabarti. I feel that, so many institutions in India and worldwide have now, created these centers for fostering interdisciplinary work. So even in IIT Bombay, now we have a center for machine intelligence and data science, where we are going to start a MS by research program and a PhD program. And the whole goal is for people to work on interdisciplinary problems, where we will try to bring together users of ML, say in some of the hard engineering sciences, with the providers or the people who work in ML core. So yeah, I mean, this is you are right. I mean, and particularly even for ML researchers, it's really difficult to keep track of the ML literature. It's just exploding, and you definitely cannot handle it all alone. I would not recommend it. It's just going to be a severe wastage of time, and you are best off collaborating. And I think the centers which many organizations are now creating is a good way to address this. So this I'm using this forum to also advertise that we are going to have a MS by research program and a PhD program in AI and data science in the Machine Intelligence and Data Science Center at IIT Bombay from autumn 2022. So please consider applying.
Yeah, thank you, ma'am, for the information. Jayati has come in. So far, DL techniques have worked great for a specific AI task. However, for AI to move towards AGI, do we think DL is the way to go, or it requires fundamentally different techniques?
Well, there is going to be, yeah, I don't know, but certainly, lot of other, work is required. Like, for example, even now in deep learning, it's very difficult to do continuous learning. And we need to be able to kind of create more modular, reusable learning structures. And a third, you need to somehow incorporate common sense. So, so common sense representation. I mean, there have been like long-standing efforts to create ontology of common sense. Now the question is, can you acquire such common sense very implicitly just by doing pre-training of language data, or just by doing enough pre-training of all the images of the world, or does one need a sort of deliberate encoding of common sense? So I think we are very far away from general intelligence.
I have two small questions. So, with reference to the word embedding example that you cited in one of the slides, you talked about multi-sense words and also context-sensitive embeddings. Can there be a role of data dictionary here? I am not sure. I'm just asking because
That's a good question too. Yeah, I feel that data dictionaries, you can generalize data dictionaries to say knowledge graphs. Many companies, they have elaborate knowledge graphs of the world knowledge. And this is another topic in which there is at least some healthy debate. There are people who believe that you can train these large scale language models and they will answer all the questions of the world. And then there are others who want to blend in these knowledge graphs of structured information with the language models to do question answering. So, I basically believe in the second part, that you need data dictionaries, you need structural encoding of knowledge, and putting everything in black box models is not the solution.
thank you, ma'am. I have one more follow-up question. You talked about model fine-tuning and catastrophic forgetting. So, what is the currently state of the art to address this particular problem?
So for catastrophic forgetting, yeah, I
Yes.
don't think, there are many papers published. People have talked about having good regularizers, and if you write to, if you send me email, you can also check on the web. If you just continuous learning survey articles, there are a lot of papers. We have tried a few of them. They don't work as advertised.
Yes. Right. Yeah, that is the point I was trying to
Yes,
ask
yeah.
to you. Yeah, yeah. Okay. Thank you so much. Deeksha has one more question. Do you think lifelong continual learning is the solution to automatic model adaptation?
If it worked, yes. Yeah. But it does not always work. Yeah.
So I think we are done and we have no more questions. So Professor Sunita, we thank you for your stimulating speech. We thoroughly enjoyed your presentation and we actually lost track of time. So I am very grateful you took the time of your busy schedule to address us. Professor Sunita, please accept our sincere thanks and best wishes for the wonderful research and for enlightening us with your
Thanks.
vast experience
Yeah.
and joining the RISE program. Thank you so much.
Thanks.
Professor Sunita, ma'am, Professor Saragopan has sent his special thanks to you for accepting to speak here. Thank you very much from our side as well as from his side.
Yeah.
Thank you very much.
Yeah. Yeah. My regards and thanks to Professor Sadhguru.
Yeah, thank you. Thank you.
Thank you.
Thank you.
So we come to the end of the session and we can break now.
Yeah, thank you very much for we had wonderful session. Now we will break here and we will join to the other sessions where there is faculty interaction. Whoever we had sent earlier videos of different faculty talking about several topics that are researched at our institute, and they will be available at the allotted slots. So please do join in the slot that you are interested in and interact with the faculty or the PhD students who are available in the booths. Thank you very much. And yeah, we can end the session.